Okay, welcome everybody to lecture 7 in ECE 560, Modern Control Theory. Before we start the lecture, I would just like to say a few words about the project. So I've given people feedback regarding their projects. Some project ideas were very vague, so I've asked for more clarifications. It's an ungraded assessment, so the whole idea is to keep you on track. So make sure you have the idea clear in your mind and you know what you're going to do, because a lot of the ideas that I saw were very general and it is not clear what the final deliverable will be and what is the eventual goal of the project. So if you're somebody who's been advised to provide more details, start thinking about how to have more concrete deliverables. If not, there are some people who are doing a pretty good job and I think they can continue working on their projects. So this is our last week before the winter recess. So try to make use of this holiday and make the maximum effort towards your projects. I think this is the right time for you um, to work exclusively on projects. Okay, we wouldn't have a homework because we already had one this week. So we will have just a quiz for next week. So try to put maximum attention on the project.
Professor, will the quiz be assigned next week, or is it going to be assigned immediately after class today?
So the quiz will be after the spring recess. So the lecture after the spring recess, I forgot the date. It's probably March 7. Let me make sure.
I think it's March 10th.
So there's nothing due in the spring recess. Yeah, so March 10, you will have the quiz due date. Okay, and then we will continue with the alternating homeworks and quizzes.
Okay, thank you.
All right, anything else you want to clarify before we start the topic today? Okay, if not, so let's start with today's lecture. Just a quick recap about what we've been doing last time. So, I mean, we saw how to design full state feedback controllers, right? So full state feedback controller design last time. And we saw that they serve many different purposes. For example, making the system stable. If it is not, so we can meet certain performance specifications or system response. We can also track a certain reference for the output. Okay, and primarily what we saw is the pole placement, right? So the whole approach is to place the poles of the closed loop system via state feedback. Okay, and I gave you a small disclaimer there that, you know, while pole placement is possible, but the state feedback may not be implementable, right? So, and the reason is because the state is not available from the dynamical system. So you have an input going into the system and an output coming out, but you do not get the state information x of t, and that's where the problem originates if you want to do state feedback. Right, so unless your y equals to x, meaning all your states are visible at the output, you may not be able to do a state feedback controller design. So let me just draw you the picture that we were looking at. So we had a system which gets some input U, and there was an output Y, right? And the problem is you want to do state feedback, meaning you want to obtain X, right? So the state X, and then you want to do a gain K next to it, and then subtract it here, right, from a reference R. So the problem is that this X may not be, right, so this thing here, this is the internal system state. May be unknown, right? So the question is why it is unknown. And the simple answer is because you do not know the initial state, right? So mainly, or let's say, so because X of 0 is unknown, so you do not know where the system started, and that's the reason why you will not be able to find X of t at any particular time t. So if you do not have that state information, you cannot use this state feedback controller. So last time we said, you know, there's a workaround for this situation, and you can actually construct an observer that gives you an estimated state, and eventually you can use that state to design the feedback controller. So today we're going to expand on that theory that we studied last time to do pole placement and how we can construct accurate observers. So here, this gain K, you can actually place the poles wherever you like. So using static gains, the closed loop poles of the system can be placed arbitrarily. And hopefully you have experienced this in your homework as well. But just a caveat here that obviously you can only do this for controllable systems only. Right, so hopefully if the system is controllable, you will be able to place its poles arbitrarily using a static gain feedback controller. Okay, so let's move on to the topic today. And that's really about the need for for an observer, right? So observer is like an estimator to estimate the internal state of the system. Okay, so what that means is, let's say you have the same old system, right? And which takes an input U here, and you eventually get an output Y from that system. So the goal of the observer is basically to take the output and the input. So there's, let's say the, if I can undo this. Well, anyway, so you want to take this here, right, the U, and you want to take the Y to come up with something called X hat, right? and X hat is the state estimator. So eventually you can use a static gain feedback using this estimated state X hat, right? So basically, okay. So maybe it's better to think of U here. So let's say the U is coming from the initial initial input U. Okay, so that's the overall picture that we want to have. Using the output and the input U, you want an observer to come up with an X hat, and eventually that X hat is used in the feedback design. And if the system is observable, so note so now comes the property of the observability of the system. So if the system is observable, then the state estimate is actually asymptotically accurate. So, which means that, let me write you the whole equation here. So state estimate is asymptotically accurate. So let's call this the state estimate X hat of T. Okay, so being asymptotically accurate means that if you take the norm of X hat of T minus X of T, right, which is essentially the square root of the summation I is 1 through n xi hat of T minus X of T, or xi of T, where I is the ith state, and you square it. This essentially goes to 0 if for T goes to infinity. Right, so as time goes on, basically your original state and the estimated state kind of converge. So that's a good estimator. And if the system is observable, this thing will happen. And today we are going to look at one possible design of an observer. Obviously, there are many possibilities and ways to construct estimators and observers, but today our goal will be to study the Leuenberger observer. Right, so it's very well-known observer design, and basically named after David Leuenberger. It's a very simple design of a linear observer or linear estimator. And what it says is the following. So it says, consider an unforced system, meaning, let's say there's no input to the system, right? So unforced or autonomous system, which means basically your U equals to 0. Then your system will be x dot equals ax, and your y is basically cx, right? That's your original system. And your observer, it's going to be a replica of the system. So let me write this here. So Leuenberger observer is actually a, okay, this is a bad place to write. Okay. So this one here is a it's a replica, meaning that you will have x hat dot equals ax hat plus L y minus y hat. And the output y hat equals cx hat. So let me draw this for you to make it more clear. Let's do this on the next page. So let's say there is a unforced system. So let's say there is a system, right, which is governed by some dynamics, and it takes some input. Now, the output of that system is y, and the observer is basically a replica of the system. So if the system has matrices A, B, then basically the observer would also have the matrices A, B, right, or A, B, C, right? So the observer will be a replica of the system, and it's going to generate an output which is called y hat, right? So if you want to write this clearly, basically here x dot is ax plus bu, and y equals to I mean, for here you let's say there is no u, considering an unforced system, and the y is cx, right? But here the x hat dot is ax hat, and your y hat is cx hat. So that's your observer. Now, so if you subtract the outputs here, so let's say there is a subtractor here, which is doing y minus y hat, then you generate an error signal, and that error signal is fed back into the observer using a gain vector L. Okay, so that's your observer design. So notice that basically you are actually using the output as well as the inputs to construct a let me just construct a estimator. So you construct a estimate of the state, and then eventually you will use that for feedback control. So maybe it's not very clear here, but if you again write the equations, the system says it is x dot equals ax y equals to cx, and the observer says x hat dot is ax hat, and y hat equals cx hat. Okay, so let's try to study the error. So error signal E is basically maybe let's call the error E in the states, the difference between the states. So let's call it as x minus x hat, right? So which says eventually if you take derivative here, it will say E dot is x dot minus x hat dot. So this is the error dynamics. Okay, so let's try to expand what the error dynamics look like. So E dot is x dot minus x hat dot. But remember that this here is ax and remember the observer has an input here. So the observer actually has an L times y minus y hat. So that's the x hat dot. So this thing here is ax hat plus L y minus y hat. Now this L is also called a output injection matrix. Output injection gain or output injection matrix. So if you try to simplify the error dynamics, what you will get is ax minus ax hat minus L y minus y hat. So if you further simplify it, it will be a times x minus x hat minus L. And remember this y is cx, and this is cx hat. So what you get is basically cx minus cx hat. Right, and then eventually you can also further simplify this. It's going to be ax minus x hat minus lc x minus x hat. Right, so you can write it as a e or let's take it common. So you will get a minus lc and x minus x hat, which can be written as a minus lc e. Right, so therefore E dot is a minus lc e. Right, so this tells you this equation tells you how the error evolves with time. Right, so this is like the error dynamics, meaning how does the difference between the estimated and the true state changes over time. So it's again a linear system of equation. So what you want is basically that a minus lc has to have negative eigenvalues, right? So this so this thing here, so this has to be Hurwitz. Hurwitz meaning all eigenvalues in the left half plane. So for the error to go to 0 as t goes to infinity. Right, so if you remember your previous discussions, basically, if A minus LC has all eigenvalues in the left half plane, then this system is going to converge to 0 as t goes to infinity. Okay, so let me show you a diagram that illustrates this evolution of the error signal. So here is the, so let's just paste it here and try to describe this. So x1 is the solid line. That's basically the original state, and x1 dashed line is the estimated state. Now, as you see that over time, the actual state and the estimated state come closer to each other and eventually become the same, right? So this convergence depends on the eigenvalues of A minus LC, because that's the error system. So if let's say the A minus LC has negative eigenvalues that are further into the left half plane, then you will have faster convergence. So meaning, let's say you may have something like this. Right? So this happens if so convergence is faster if the eigenvalues of A minus LC are further into the left half plane. Okay, so let's see what is happening here. Basically, you had a system, right, with input U and output Y, and the problem is x of t is not, or let's say it's unknown. The reason why, because x of 0 is unknown, right? But however, if you have observer is a replica of the system. So observer, you have the same input U, you have output Y hat, and now the X hat is known because any arbitrary initial condition can be used. Right? So you can arbitrarily select X hat of 0 can be used. Right, so if you select a different initial condition, your estimated state will be different. right? For example, in the same system, if you select a different initial condition, you may, oops. So you may come here. So different x hat of 0. So you are free to choose any initial condition, and you will have a different estimated state. But the best part of the story is that over time, whatever you pick, the whatever initial condition you pick, the estimated state is going to converge to the actual state of the system. Right. So even though you do not know what is the x1 or x, but x hat is going to approach x as t goes to infinity. And how quickly it goes to convergence depends on how negative the eigenvalues of A minus LC are. So this is a very simple observer proposed by David Leuenberger, and that's why it's called a Leuenberger observer. So let's quickly write down a fact here. So if the system is observable, then we can arbitrarily assign eigenvalues of A minus LC by a suitable choice of output injection matrix L. So now let's go and see a extension of this system, which is called a forced system. So now we have a input U on top of the system. Right. So let's see how the observer looks like in a forced system. So we already saw the unforced system, which is simply A minus LC, but if a system where you have a non-zero input U, meaning x dot is AX plus BU, and right, so this is your system. Y is CX, and the pair AB is controllable, and the pair AC is observable. Right, so we are considering a system which is both controllable and observable. Then the Leuenberger observer is going to be of this form. So you will have x hat dot will be A x hat plus BU plus L y minus y hat. Okay, and the output y hat will be C x hat. Okay, so let's draw a diagram there. So you have a system, right, that has some input U, and there's a output Y, right? But you do a you have an observer which is exact replica of the system. So that gives you an output y hat. And this y hat is actually subtracted here to get the different signal, and then this different signal, there is a gain L. So the observer basically takes this input signal U here, and on top of that there is another input which is L times y minus y hat. So to be more precise, let's add a the matrix B here, right? So basically you have BU and L times y minus y hat as input to the system. So now if you look at the equations of the observer, basically what you will get is x hat dot is basically ax hat plus b so from the observer, basically notice that you will get a x hat, right? So that x hat will have a gain k, and that gain k is actually going back to or minus k, and that goes back to the input u. So if you have this type of system, then though your u is minus k x hat and plus L, oops, plus L, again, this will be cx minus cx hat. So you will get x hat dot is, if you simplify it, it will be a minus bk minus lc x hat plus ly. So let's keep this as y here. So you will have plus ly. So that's your equation of the observer or estimated state dynamics. Again, you want to look at the error state. So let's say E is x minus x hat, right? Which tells you E dot is x dot minus x hat dot. So E dot is x dot. So x dot was ax plus bu, and then we have minus ax hat plus bk x hat minus lc should be plus lc x hat, right, and minus ly, right? Okay, so Obviously this y is cx. So if you try to simplify it, you will get E dot equals and by the way, this u is minus kx. So this will cancel with this. And what you're left with is a times x minus x hat minus LC x minus x hat. Yes.
Minus k x hat.
The u, yeah, right. Yeah, that's how they will cancel out. So you will get a equation here which says E dot is basically A minus LC E. Right? Again, it's regardless of the input U. So even if the system is forced or unforced, basically your error dynamics have the same form. So error again evolves as A minus LC times E, which tells you that this A minus LC has to be Hurwitz if you want your system states to converge to the original state. So if you want your observer to come up with accurate estimate of the original state, your A minus LC has to have negative eigenvalues. So one more diagram before we start with the design of observers and that closed loop system. So you had your original system. So basically this diagram sums it up all. It's a little complicated to simulate this, but eventually I think you will start to follow this. So there is a original system that generates an output y. Now what you're trying to do is you take the output and there is a observer, right? The observer can help you get an x hat, right? And you multiply it with minus k and you feed it to the original system. So your u here is minus k x hat, right? That's what we were saying originally. And basically the observer also takes a BU as the input, right? So essentially what is important is the fact that this piece here is called a dynamic output feedback. And remember previously we were simplifying the stuff and saying, you know, there's just a gain k that multiplies to the x, but we realized that x is not even it's not observed, so that's something we cannot do. Now what we're trying to do is we attached an observer that helps us give an x hat, and that x hat goes back to feed the input. Now remember, this is a dynamic observer because the observer is actually a dynamical system, right? So this piece is actually a, remember so there's an observer or observer is basically, if you want to be precise, AX hat plus, right, whatever, maybe let's not write this here, but if there's a output Y hat, that Y hat is, you subtract it, right? So you actually, so there is a, there's a Y, which is getting subtracted by Y hat, and then there's an L. This goes into the system. Or let's say this is a system replica. Right, and then this generates a Y hat. Right, so that's a, you know, this thing here is the observer. Right, so this is a dynamical system in itself, and that's why we will call this a dynamic output feedback instead of a static feedback. And next step is, how do we analyze this dynamic output feedback system? So if you look closely, the overall closed loop system can be described by the following equations. So previously we just used u equals to minus kx, and that was the closed loop system, and we realized our closed loop system equation has a minus bk as the important matrix, and that has to be Hurwitz, meaning its eigenvalues have to be in the left half plane to be stable. But now let's say our x dot is ax minus b k x hat, right? So if you want to be more precise, x dot is ax plus bu, right? But you are saying b is u is minus kx hat, so you will have ax plus b and a minus kx hat here. So your equation eventually becomes x dot equals to ax minus bk x hat. And let's look at the second dynamics, which is x hat dot. It is it's ax hat plus bu, right? But the u here is minus lc, right? lc it's actually ax hat plus bu plus l y minus y hat, right? So this will be ax hat plus remember b is the input is minus is a minus k x hat. It's minus k x hat plus L. So y is your cx. And then you have minus LC x hat. So if you simplify this, you will get A minus BK minus LC x hat plus LC x. So that's your, so let's say your x hat dot is A minus BK minus LC x hat plus LC x. So now you have two dynamics going on in parallel. One is x dot and the other is x hat dot. And if you write it in the form f of a vector, what you will get is so these dynamics can be written in matrix form as, let's say, x dot and x hat dot. So if you write this in the form of a matrix, here we will have x and x hat. So by looking at the two equations that I wrote in the previous slide, you will eventually get A here minus BK here, LC here, and A minus BK minus LC here. Right, so this equation you could call A star. So basically your x dot x hat dot is some A star x and x hat. Now to convert this into a new state space. So let's do a small trick here that will help simplify the system. So we can transform the augmented system to new coordinates, and that coordinate basically says you have x and e, which is the error. So x and x hat is some, let's say this goes to a new coordinate system where you just have x and e. E is the error. So let's say there's a transformation matrix T that does this trick, meaning you have x and x minus x hat. So this T matrix can be as follows. It can be identity here, 0, identity, and minus identity. So if you use this transformation, your vector, the augmented state vector x and x hat will go to x and a vector of error signals, x and e. Right. So I mean here, note that basically T times X and X hat is going to give you identity 0, identity minus identity times X hat. So if you simplify this, you will get X here and X minus X hat, right? So this is the T that basically transforms this to a new system. So if we use this transformation, so we're using transformation T, we will have a system where X dot E dot is some A bar, A star bar times X and E, where your A star bar equals T times A star T inverse. Right, so from here, it turns out your A bar star is a matrix which is A minus BK 0 BK and A minus LC. It's a little bit tedious here, but eventually the result is really beautiful, and it's a very important result in a control theory. So remember, right, this is a triangular matrix. So this really is a lower triangular matrix, and eventually the system will be so X dot E dot is basically A minus BK, A minus LC here, X dot, the X and E. Okay, so now if you have this, basically your characteristic polynomial. Let's go to the next page. So your system eventually reduces to this system. And the characteristic polynomial of this system is basically, by definition, it is the determinant of this matrix. Okay, which is essentially, because it's a triangular matrix, so it's going to be the product of the determinants of the diagonal matrices. It's A minus BK times determinant A minus LC. Okay, so that's the beauty sitting right here. So we have two pieces. So A minus BK and A minus LC are separated. So it implies that the closed loop eigenvalues are basically the roots of determinant of Si minus A minus BK right? So these roots and a union, the roots of determinant as I minus A minus LC. Right, so if you look at this closely, basically this piece here, these are called controller poles, and these are called the observer poles. So this idea here is also referred to as the separation principle. So this it's a very famous idea. It's called a separation principle, and that really simplifies the design of observer and controller separately. So it separates controller design and observer design, and this principle is only true for linear systems. So this is true for again, linear systems are great because separation principle holds. So to put it simply, if you haven't really been following what is going on, basically the closed loop system says that you have to basically look at the A minus BK minus LC, right? So the separation principles tells you that you can actually break it down to design of two different things. One is A minus BK, and the other is A minus LC. So this piece is called controller design. And this piece on the right side is called the observer design. So let me take a moment and go back to talk more about it. So if you see the original system, the closed loop system, for a dynamic output feedback controller, we came up with the two equations. One is the dynamics x dot, which is ax minus bk x hat. So you see that there is an x hat sitting here, which means you cannot just consider only x. We have to look at the dynamics of x hat as well. So, okay, we next go on to see how x hat evolves over time. And we saw that this is coming out to be this expression. And this x hat is a function of x and x hat. There's two variables here. Now you can combine them in a form of in a matrix, right? And then it turns out to be this matrix here. Now the thing is, you want to get rid of the x hat and want to convert it into something related to the error dynamics, right? So what we do is use a transformation. We use a small trick here. So we transform x and x hat to a new system of coordinates where it is x and e. And it is simple to do it because a simple transformation matrix T, which looks like the following, will transform this system. Okay, so using our previous knowledge of similarity transformation in linear systems, we said, okay, if T is this, then basically your A star will go to some A bar star, and that can be computed using this T times A star times T inverse. That's the standard conversion when you have a similarity transformation. So A bar star turns out to be this beautiful structure matrix, which is lower triangular. And now the idea is that you want to make sure that the eigenvalues of this system is in the left half plane. So luckily, because of this special structure, the eigenvalues of this A bar star is going to be the union of the eigenvalues of this and this piece here. So if, yeah.
The proof of why is it as I minus I minus A minus B. Actually, it should be as I minus A plus B.
Yeah, okay. So this is a bracket here. Yeah, that's a good, okay. Let's, oops, thank you. So an SI minus A minus LC, yeah. So, so you want to make sure that the poles of both A minus BK and A minus LC are within the left half plane. And we have already seen A minus BK in the controller design. So remember, we called this piece as the controller poles. And using that similar analogy, we will call the A minus LC poles as the observer poles. Now, by looking at the structure, it turns out that the design of the K vector and the L vector can be actually separated from each other, because K and L doesn't have to do anything with each other. They only depend on AB and AC. So, and eventually the poles are going to be the union. So there's something called separation principle. And this essentially is saying that designing, the design of, or let's say, placing of this may be harder. So we can split the placement into two simpler pieces. So, so what turns out is that the poles of A minus BK minus LC are actually the combination of the poles of A minus BK and the combination of the poles of A minus LC. So, so that's the two different dimensions that evolve from designing an output feedback system. If you want to use static gains to modify the location of the system poles. Now, one observation is that obviously you are designing an estimator and using that estimator to make the system stable. So you're using X hat, feeding it back to the system input. So if the X hat is inaccurate, then that may create some problems in your system stability. So there's this one important note that observer poles should be at least 2 to 5 times, or let's say this 5 to 10 times um, 10 times larger, or 5 to 10 times the poles, the controller poles, so that the system performs accurately. So what do I mean by this fact? So I'm trying to say that the U is minus kx hat. So if x hat is not accurate, then the controller will perform poorly. So if your observer poles are larger, then the observer will quickly converge, and hopefully that is going to be fed as the input to the feedback controller, and the system should work much better. So what I mean is, if you have a real imaginary axis, and let's say you have, these are the controller poles, then your the observer pole should be much further into the left half plane. So observer poles must be farther into the left half plane for quick convergence of x hat to x. Okay, now so dynamic output feedback controller, it actually gives you the same performance, gives roughly the same performance as the non-implementable full state feedback controller. If the observer poles are placed far enough into the left half plane. Okay, so in other words, the kx hat is approximately equals to the kx if the observer poles are appropriately placed. Okay, so one last comment here before we will try to do an example is, so remember the system has to be controllable and observable. For all the story to be valid, your system has to be controllable and observable. If that's not the case, then that there are decompositions that allow you to split the system into subsystems which have those properties, and then you can try designing a observer and controller to actually do a dynamic output feedback. So with this simple idea of using a replica of the system, we see that an estimator can be constructed that asymptotically tracks the original state of the system. Now I'm going to do an example here that helps you identify the design of a dynamic output feedback controller. So the question says use the separation principle to design an observer-based output feedback controller for the following LTI system. So if imagine you have a system x dot equals 0, 1, 1, 0, x here plus 0 minus 1 u, and your y is 1, 0, x, then the question is, you want to do an observer-based output feedback controller, and you were given that system poles to be placed at minus 0.5 plus minus j 0.5, and observer poles to be placed at minus 1 plus minus j. Right, so let's say we are asked to place the observer poles at least twice the controller poles, or let's say the system poles. So now the separation principle has told you that the controller poles is basically trying to place the poles of A minus BK, and the observer design is basically to place the poles of A minus LC. So you are going to use the same pole placement procedure that we saw last time, and you're going to repeat it on A minus BK and A minus LC respectively to eventually achieve this. And once you have designed K and L, you just combine them together and the system is going to perform exactly as you expect it to be. Right, so here there is a dynamic output feedback coming into the system. There's no static feedback. So even though you're not able to obtain the exact state information, the system is going to estimate the state itself and result in the output that is desired. And you can basically test in MATLAB whether this happens or not. So let's start with the controller design. So I'm going to do a quick, solution here. I think you're already familiar with the process. So if you want to do a controller design, you start off with the first step, which says, what is the desired characteristic polynomial? Of A bar minus B bar K bar, right? So that turns out to be S plus 0.5 plus 0.5 J, S plus 0.5 minus 0.5 J, right? And this turns out to be S squared plus S plus 0.5. So, all right, so if that's the first step, then what is the characteristic polynomial of a currently that's basically the determinant of SI minus A. So it's going to be the determinant of the matrix S minus 1, and S. So it's basically S squared minus 1. Okay, so essentially you can say that your A bar is in the canonical form, right? So you have 0, 1 here, and this is coming from the coefficients of the of the here. I mean, this is minus, or this is A0 bar, and then A1 bar equals to 0, right? So this turns out to be 1 and a 0. And the B bar is standard, which is 0 and 1. Next step will be to find the controllability matrix. So which is a B. And if you do it, it turns out to be 0, minus 1, minus 1, 0. After that, we do the controllability of A bar, B bar, which turns out to be B bar, A bar, B bar. And it's again 0, 1, 1, 0. So the transformation matrix that is going to do this canonical conversion is going to be C AB times C A bar B bar inverse, and so essentially it's 0, 1, 1, 0. Oh, so I'm making a mistake here. So the bar is here. And the next one is 0, minus 1, minus 1, 0, whole inverse. So what you get is a new matrix minus 1, 0, 0, minus 1. Okay, so you have this transformation, and the final step is to compare the coefficients of A bar minus B bar, K bar. So if you look at this, this is 0, this is 1. And if you go and from the desired characteristic polynomial, you can write this as a minus 0.5 and minus 1. Now you have to compare this with the standard canonical form, and remember that in the form of minus a0 bar plus a1 bar and then minus a1 bar plus the standard form. So it tells you that a0 bar plus k1 bar is 0.5 and a1 bar plus k2 bar is 1, right? And remember, this is coming from the previous a bar matrix. This is first one is -1, the other is 0. So so following this, basically your k1 bar will be 1.5 and your k2 bar will be 1. So basically your k bar is a vector 1.5, 1. So standard controller design stuff. Next step is to convert the original coordinates, which is k is k bar times t. So by the way, k is actually a row vector. So it's a 1.5, 1. So if you use the transformation t that we computed earlier, it's -1, 0, 0, -1. What k eventually will come as -1.5 and -1. Right, so that's your controller gain. Okay, so perfect. This is something you already are familiar with. But the next thing we have to do is to do observer design. And the good thing is we can do it independently of the controller. So the goal is to place the eigenvalues of A minus LC at -1 plus minus J. Right, but remember, the caveat here is that L, it's not like B and K. So C is a 1 cross n vector and the L is an n cross 1 vector. Okay, so the problem now is, your process that we've been doing for controller design is a little different from this. So if you want to reuse that process, we will do a new trick, which is saying, if you want to place the eigenvalues of A minus LC, it is equivalent. This is the most important thing. It's equivalent to placing eigenvalues of A transpose minus C transpose L transpose. Right, so C is going to be like your B, right? And the L transpose is like your K, gain vector, right? So you can use the same methodology, but you have to use it on the transposed system. Now let's try to do it. We can actually say at -1 plus minus j. So if you try to do this, basically you will start off with the same step here. So maybe let's do a characteristic polynomial of A. It's going to be the same as a characteristic polynomial of A, because that's by definition, characteristic polynomial will be the same no matter you transpose it or not. Now, basically, this is going to be determinant of Si minus A transpose. So if you do it, you will again end up with S squared minus 1, which is the same as the previous one, but just to show you the computation this time. And the next thing is the desired characteristic polynomial. So it's going to be S plus 1 plus j and S plus 1 minus j, which turns out to be S squared plus 2S plus 2. So the canonical form of canonical form is A bar transpose. And it's the same, 0, 1, and you have 1 and 0. Right, so 1 and 0 again is coming from here. These are the A0 and A1 for the negative sign. And then the C bar transpose, instead of B here, we will have a C transpose. So this will be 0 and 1. Now, next step is to find the controllability of A transpose C transpose, right? So remember, we can actually contrast with AB, right? So instead of doing a controllability matrix of A and B, you will do controllability of A transpose C transpose, which is exactly equal to saying observability matrix of A and C. But let's not get confused too much. We want to reuse the thing that we have learned, and so this basically is going to be the C transpose A transpose C transpose, right? Just like a BAB. Okay, so this turns out to be a 1001. Now the next thing is the controllability of A bar transpose C bar transpose, which is again C bar transpose A bar transpose C bar transpose. And this turns out to be 0, 1, 1, 0. Then we come to the transformation matrix. So this T is C A bar transpose C bar transpose. times the controllability of A transpose C transpose inverse, and which is going to be 0, 1, 1, 0 times 1, 0, 0, 1 inverse, and it turns out to be simply 0, 1, 1, 0. Okay, now now the next step is basically in canonical form. A bar transpose minus C bar transpose L bar transpose. It's going to be 0, 1, -2, -2. So we want to compare it with the standard form. So standard form will be minus A0 bar plus L1 bar, and then minus A1 bar plus L2 bar. So there's no K here. There's only L1, L2. So by comparison, A0 bar plus L1 bar equals to 2. A1 bar plus L2 bar equals to 2. And this thing here is basically -1, and this thing here is 0, which you can go and look back from the previous slide. So this turns out to be that L1 bar equals to 3 and L2 bar equals to 2. Right, so eventually we can say L bar is, or we can say L bar transpose, right? It's 3 and 2. So finally, the conversion to original coordinates. Where L transpose is going to be L bar transpose times T. So this is 3, 2, and your T is 0, 1, 1, 0. So it turns out to be 2, 3. So L transpose is 2, 3. So L is basically the vector 2, 3. Okay, so this is the so observer gain, or we can say the output injection matrix. Okay, so finally, you have basically found K and L. And if you implement it in the form of a dynamic output feedback controller, then you are going to have the observer poles and the controller poles placed as you wanted in the question. So the dynamic output feedback controller is described by the vector K equals -1.5, -1, and L equals 2, 3. Right, so that's
Professor,
yes.
Professor, can you explain what is the purpose of us transposing the matrices?
Okay, so let's go back one step and look at the observer design goal. So the goal is really to place the eigenvalues of A minus LC at this, right? So previously we know how to place the poles of A minus BK, right? This is something we already know, right? You have done it in your homework. We spent the last lecture figuring out how to do this. Now, if somebody tells you, can you place the poles of A minus LC and the orders are basically or the dimensions are different. So remember, the A and the B are already given to you. But in this case, A and C are given to you. So if you want to kind of reuse what you already have, I said there's one trick. So the trick is that eigenvalues of A minus LC are the exact same eigenvalues of A transpose minus C transpose L transpose. Right, so let's look at this one more time. So A minus LC, where A is given, C is given. If you transpose, you will get A transpose minus C transpose L transpose. Do you see this?
Yes.
Okay, so if you see this, this has a one-to-one correspondence with this. You know, this is like your B, this is like your A, and this is like your K. So what I'm suggesting is, in order to reuse your previous process, let's do the pole placement on A transpose and C transpose. Right? So instead of doing A minus BK, you will do A transpose minus C transpose L transpose. So you can rename them, but the idea is the same. So we started off with a characteristic polynomial of A transpose, which turns out to be S squared minus 1. Then we went on to the desired characteristic polynomial, which comes from the pole locations. So it is here. Now, canonical form of A bar transpose, right? Remember, we are dealing with a transposed word now. So instead of looking at canonical form of A, we will look at canonical form of A transpose bar. So that's going to be like this, where 1 and 0 are coming from this expression. Okay, and instead of your B bar, you are saying your C bar transpose is of this form. Okay, and the next step, previously we used to do controllability of A and B, but now we are going to do controllability of A transpose and C transpose. And by definition of controllability, it's going to be this vector here, C transpose, and then A transpose times C transpose. Just like we did B and AB. So same thing with the canonical form. This is something that we get, and using these two, we get the transformation, similarity transformation T, which is pretty standard. Now, You just have to remember your A is replaced by A transpose and your B is replaced by C transpose. And you're doing the exact same thing. So when you go to the next step, basically instead of saying A bar minus B bar K bar, you are looking at this new word. Instead of B bar, you have C transpose bar, and K bar is L transpose bar. And this is coming from the desired characteristic polynomial. And again, the same idea. But here, instead of the K vector, you have L1 and L2. You're not in the K world. So the rest is standard. You compare these coefficients and come up with L1 and L2. So, and then instead of saying, the gain vector K bar is something, you say L bar transpose is this. And again, here it's like K is like K bar times T. So K bar is 3 and 2. Transformation is like before. So you get L transpose bar to be L transpose to be something. And then if you want to find L, it's just you convert it from a row to a column. So is that clear now, or do you still have confusion?
No, it's clear. Thank you.
Yeah, I mean, we can do another example to make it better. Yeah, probably this. Let's do another example. Maybe a bigger example. So consider the LTI system with the 3 states. So you have x1 dot, x2 dot. It's going to be minus 25, 0, minus 0.5, 0, 0, 0, 46, 0.296, 0, and a, oops, there is a 1 here. You have x1, x2, x3 here, plus 5, 0, 0, u. And your y is 0, 0.02, and 0, x. So the question is design and output feedback controller. With the controller poles at -1 plus minus j, comma 10 or minus 10. Right, so these are your 3 controller poles, and observer poles at -5 plus minus 2j and -4. So these are your 3 observer poles. So let's start with the controller design. So the beauty is, maybe I should write it here. So because of the separation principle, we can design the controller and observer separately. So in other words, place the poles of A minus BK and A minus LC independently. So we can start with the controller design. So the first step may be to look at the characteristic polynomial of A, which is the current situation. It's essentially the determinant Si minus A. So it turns out to be S cubed plus 25 S squared plus 23.148 S. And then the desired characteristic polynomial is going to be the combination of the three poles. So you will have S plus 10, and then S plus 1 plus J, S plus 1 minus J. And if you simplify this, it will turn out to be S cubed plus 12S squared plus 22S plus 20. Okay. And now from here, actually, you can directly see that your A bar is the canonical form. So canonical form always has 0, 1, 0, 0, 0, 1. And then you have a 0 here. You have minus 23.148 here and a minus 25 here. And B bar is standard, so it's 0, 0, 1. Okay, great. So next step is to look at the controllability of A and B, which is in this case we have three states. So you will have B, A, B, and A squared B. So it turns out to be, I'm just going to put it here because the computations are a little long. So you get eventually 5 minus 125, 300.93, 0, 0, 23.15, and 0, 231. Oh, so this is 231.5. And minus 5787. Then the controllability of A bar, B bar, which is B bar, A bar, B bar, A bar squared, B bar. And eventually this turns out to be 0, 0, 1, 0, 1, minus 25, 1 minus 25, 601.9. 852. And then again, standard procedure, the transformation, similarity transformation is C A bar B bar times the controllability A B inverse, and computed using MATLAB, turns out to be 0, 0.0043, 0 here, 0, 0.043, and 0.200. Okay, perfect. So we have the transformation. Now, the next thing is to compare A bar minus B bar K bar. So it's by standard using the desired characteristic polynomial. Turns out to be minus 20, minus 22, minus 12. And remember, this has to be compared with the standard form, which is minus A0 bar plus K1 bar, and then minus A1 bar plus K2 bar, A2 bar plus K3 bar. Right, so by comparison, basically A0 bar plus K1 bar is 20. This is 22, and A2 bar plus K3 bar equals 12. And this was 0, this was 23.148, and this is 25. Okay. So if you use these numbers, you will get your K1 bar is going to be 20. K2 bar is minus 1.148. K3 bar is minus 13. So your K bar is actually the row vector. This is 20 minus 1.148 minus 13. And the next step is just standard K is K bar T. So if you use it, you come up with minus 2.6, 0.0864, and 0.005. Okay, that's done for the controller part here. And next step will be to go to the observer design. So again, goal is to place eigenvalues of A minus LC at -4 and -5 plus -2j. So again, I will use the same trick. So it's really equivalent to placing poles of A transpose minus C transpose L transpose at -4 and -5 plus -2j. So we're going to use our previous calculus to do this, and I'm going to do it in a short way. Basically, if you see that the A transpose will have the same characteristic polynomial, so your A bar transpose will be exactly the same. and your C bar transpose is going to be the standard 001. And then the desired characteristic polynomial is s plus 4, s plus 5 minus 2j, s plus 5 plus 2j. So it simplifies as s cubed plus 14s squared plus 69s plus 116. Then we can compute the controllability of A transpose C transpose, which is by definition C transpose A transpose C transpose A transpose squared C transpose, and what we get is 0.9259. You will basically see more examples as practice in your homework, which will be the second week after the winter recess. So this is basically your C of A transpose and C transpose. Then the next step is A bar transpose, C bar transpose. So again, by standard definition, A bar transpose. Maybe let's go to the previous. A bar transpose, C bar transpose, and then A bar transpose. Let's see whether I can get rid of this. Okay. C bar transpose, and so this turns out to be a matrix 0, 0, 1, 0, 1 minus 25, 1 minus 25, 601.852. And next step again is the transformation matrix T, which is controllability of A bar transpose, C bar transpose times controllability A transpose, C transpose inverse. If everything is computed correctly, it's going to be negative 1.1, 0, 0, negative 27, 0, 50, 650, 50, and minus 1250. Okay. Perfect. So last step is the comparison basically. So A bar transpose minus C bar transpose L bar transpose coming from the desired polynomial is 0, 1, 0, 0, 0, 1, and minus 116, minus 69, minus 14. Right, so remember this by comparison, it's going to be minus A0 bar plus L1 bar. This is minus A1 bar plus L2 bar, and then minus A2 bar plus L3 bar. So we are left with the comparison. So A0 bar plus L1 bar is 116, A1 bar plus L2 bar is 69, A2 bar plus L3 bar is 14. This coming from the previous page is the values 0, 23.148, 25. So what you get here is L1 bar is 116, L2 bar is 45.852, L3 bar is minus 11. So your L bar transpose is going to be 116, 45.852 minus 11. And the final step is converting to original coordinates, which means L transpose is L bar transpose T. So if you do this, you will turn, it will turn out to be minus 8263, minus 550, and 16043. Right, so eventually L is going to be a vector which has these gains. So for this problem, you can say that the dynamic output feedback controller can be described by the vectors. K is minus 2.6, 0.0864, 005, which we computed during the controller design part, and the L, which is a column, minus 550, 16043. And that's the end of this problem here. Okay.
Sorry, Professor.
Yeah.
In feedback control design, we use Ackermann formula, but for this part, we cannot use the same formula as well, and we should go through those steps.
No, you definitely can use Ackermann's formula. Right, so the whole idea is to do pole placement for A minus BK and A minus LC, or if you want to basically do pole placement for A transpose minus C transpose L transpose, right? So you can obviously use Ackermann's formula on this or this.
Okay, thank you.
But again, I think it is not that simple. It may be only simple for MATLAB or computers to do it, but if you are doing it yourself, maybe I think this coefficient comparison may be an easier way to do it. But it's up to you. I think both will give you correct results. And remember, these don't have to be unique. Right, so if you recall, the Ackermann's formula is requires you to come up with a I mean, if the system is not controllable, then you can use some arbitrary rows. So there's some how to say non-deterministic elements there. So my point is that you can actually have different gains that can actually do the same placement of poles. Right, so people can have different answers and still have the same eigenvalues. Okay, I'm going to now quickly summarize what we have talked about. And I hope you guys appreciate the idea behind dynamic output feedback and the really useful separation principle that has made it very convenient to design a controller and observer separately, and eventually you can use them in a connected topology for feedback control. And I will again draw it one more time to simplify the understanding for everybody. So today the main topic was observer design, and the idea is that it helps to estimate the state of the system. So helps to estimate the internal system states even when it is not directly visible. At the output. Right? And a natural question to ask is, why can't we solve for x of t, right? For x of t, since it's the linear system. So the answer is basically because the initial condition is not known. It can be different. So x of t solution depends primarily on x0, right? So if it's a pendulum system, right? So if you start here, you have different behavior. If you start here, obviously you have a different behavior. So x really depends on what is the initial condition is. Even though you know the dynamics, then it is not helpful because you do not know the initial condition x0. Okay, so question number 2 is how does the observer help? Since it is also a replica and the simple answer is so we can use arbitrary initial condition for observer and using y minus y hat as the input, we ensure that x minus x hat goes to 0 as t goes to infinity. So maybe I can specify it as L times y minus y hat. So for the observer, you use any arbitrary initial condition x hat of 0, and obviously it is going to generate a new output y hat. So you try to subtract the outputs and feed it back to the input, and in that closed loop system eventually ensures that x and x hat are going to be the same at as t becomes large and large. So it's asymptotically accurate, and that's the beauty behind estimation of the signal. Okay, now the question is, we can have special cases. So if y equals to x, right, that means we don't need any observer. Right, because the system states are available at the output. So because we have the states exactly, then we can, feed it back using static gain feedback and make the system overall stable. Now, for observer design, we saw that one possible construction of the or for state estimation is the Leuenberger observe. And what it says is basically your x hat dot is a x hat plus bu plus L times y minus y hat. So that's the way you construct it. And we have seen that eventually, this u equals to minus kx hat, and the matrices L and K can be designed in the using pole placement, right? So this is the observer gain, and this is the controller. Right. So if you're able to design the K and L appropriately, then the x hat dot has this form, and you basically construct this architecture, and your output y is going to perform as you have initially designed the system to behave. Okay. After this, we saw another important aspect, which is called the separation principle. Right, so remember these important ideas allows separate construction of the controller and observer. So it kind of reduces the complexity of the system. Then we saw that the pole placement procedure can be reused. So it can be strategically reused in the design of both the observer. And finally, using a appropriate appropriate gain gain vectors K and L, the desired performance objectives can be achieved. Right, so how do you achieve those objectives? Again, you see, basically, you have to construct a system in the following way. Basically, you will have your original system, which has x dot equals to ax plus bu, right? And well, instead of saying this, maybe I will say this is your system. And then this is the output y. What you try to do is you create a replica of the system, right? And here you have unknown x0, and here you have arbitrary x hat 0, right? So basically, because of this, you can actually come up with a x hat of t, and that can be used as a with a gain k here, and fed back to the input. So there's a input u, which is, let's say, minus k here. Right, so if you have minus k, you can feed it back to the system, and your original u was also fed here, right? But remember that, okay, let me, so this minus k x hat is fed to the both systems, but your output y hat is subtracted here. So you have y minus y hat. This goes through a matrix L, and that is fed back as the input here. Right, so I hope everybody is kind of getting this. So I'm going to say that this piece here is something that you call the dynamic output feedback. Okay. So instead of the standard, static feedback, if you had this system, this is y, and this is, you had x, right? So if you have minus kx, so this is called a static feedback, and this is called static state feedback. Remember, and it's not implementable. Again, the reason why not implementable, because you do not know the initial state, and hence this thing here is not possible. However, this is possible because, oh, how do I undo this? Okay, I screwed up. So this was the I think I had this, right? Yeah, so now basically in the observer case, you can actually have full state information. Estimate. Hopefully this estimate is accurate based on how you design your L. So the better the L, the quicker you will converge to original state X. And then this is fed as with a constant gain K, and okay, let me just be more precise. This should be minus L here. Okay, so this is the place where K and L is used, and then your system is going to perform in the way it should. All right, so that brings us to the end of our lecture today. We are going to have a winter recess next week, so no lecture, no assignment. I want you to focus on your projects, and my impression from the proposal ideas is a lot of people have do not have clear ideas of what they are going to do, and some people are not taking it seriously. So remember, project carries a significant weightage of your grade, and I don't want to find plagiarized work. If you copy from somewhere and present it to me, it's going to get caught, and I mean, I'm going to penalize you heavily for any plagiarized work. So don't try to copy. The project is an opportunity for you to do some thinking, to come up with original work. So even though the work is marginal, it's not significant, but at least it has to be your own work. If you copy from somewhere, then that may result in a problem. So don't come to me afterwards saying, I did a great project and I didn't get any grade and things like that. If I catch you copying from somewhere, you'll have to see the consequences. So hopefully everybody is going to take care of that and come up with a great project. Any questions before we end the session? No questions? Okay, so if not, then feel free to send me an email if you want to discuss something. And I hope you all have a relaxing winter recess. I'll see you after 2 weeks.
Thank you, Professor.
Okay.
Thank you, Professor.
Thank you, Professor.